Hi Falcons. Today what I'm going to show you is another example of the atomic emission spectrum. In a previous video I showed you this using gas tubes, where we took a gas tube and energized it with electricity and showed you the various spectrums that they would produce as those electrons and those atoms jump to an excited state and then release photons as they return to the ground state. Today I'm going to show you a similar concept, but instead of using electricity as my energy source, I'm going to be using a flame, a Bunsen burner flame. So what I have here are some Q-tips. These Q-tips have been moistened for two reasons. Number one, so that when I place them into the different salts, the salt will stick to it. Okay? And then number two, which I can demonstrate for you now, is to show that when they're wet, they don't light on fire. Now if I leave it in here long enough, eventually it's going to turn black and start to burn. But right now, all that's happening is the water's being heated, and when all the water's heated off, then this will eventually start to burn. The point of that is just to show that the Q-tip is just kind of a control. It's a method for getting the salts into the flame, but it's not, you're not seeing burning Q-tip throughout this lab. So this first salt that I have is lithium chloride. So I'm going to just take a little bit of it, dip it on the end. So you can see here there's some white salt crystals of lithium chloride. When I place it into the flame is going to serve as an energy source. And that energy source is then going to cause those electrons to jump from the lithium atoms to jump to higher energy levels and then emit photons as they return back down. Now obviously the lithium has more photons that it's emitting in the red range, which is why that's the overwhelming color that you see. If you could look closely at this, you can see that it's actually not burnt. That's because the salt itself is not combusting. It's not a combustion reaction. The atoms in there are just becoming energized and then releasing that energy as photons of light that you're able to see, the ones that are a part of the visible spectrum. Each element is going to have a different signature. This one, for example, is sodium chloride, table salt. Okay? Sodium chloride is actually a very bright emitter of light within the yellow range. Okay? This is why, for example, if for certain street lights, they actually use sodium gas vapor because it's a very bright light, and so it's an excellent emitter. If you were to mix sodium with one of these other ones, you would actually primarily see only yellow color because it emits so many photons in that yellow range of the visible spectrum that it would drown out the others. Another interesting side note with this is they often use this in street lights because it doesn't affect nocturnal animals, because it only emits specific wavelengths, so that scientists believe that because it only emits specific wavelengths, it doesn't interfere with their normal day-night cycles when we have all these street lights throughout a town. It can be an ecologically friendly way to provide light for people without interfering with all those nocturnal animals. This next one is strontium chloride. Strontium chloride is pretty famous if you've ever seen a road flare. So you can see a pretty famous, that kind of red road flare light. Again, it's going to emit photons all throughout the visible and infrared and ultraviolet spectrum, but the ones that you're seeing are primarily in that red and orange range. So again, strontium chloride. The last one you're going to see is copper chloride. Copper chloride is going to emit a kind of a blue-green color. Interestingly, going along with this, one application of all of these is use in fireworks. When you see a firework, they have little pellets in there that contain various ones of examples of these different salts that can then, when the explosion from the firework acts as an energy source, it energizes these salts, and those are the colors you'll see. Interestingly, when next time you look at fireworks, you might notice that the blue is slightly less bright than the other colors. And if you look at this, you can see that the copper chloride has actually turned black. It decomposes at a lower temperature than these other salts, and therefore can't withhold or withstand as much energy before decomposing, so those blue lights aren't as bright as the other colors. Again, this is all an example of that atomic emission spectrum. It's atoms absorbing energy and then releasing it as photons of light, some within the visible spectrum, some outside of that, but that's what's responsible for what you observed today. Thanks, Falcons. Have a great day.